Glaciers, ice that has lasted for millions of years, have started changing rapidly, and it's kind of terrifying. Around the world, these enormous rivers of ice are retreating, advancing, and sometimes vanishing completely. Some glaciers are melting at surprising rates, while others stubbornly cling to colder climates or high elevations, slowly moving forward. Some changed slowly, carving valleys and ridges over the centuries, while others surged suddenly, reshaping landscapes and leaving behind large deposits of rock and debris. Glaciers are more than just ice. They are living, dynamic parts of our Earth. They shape mountains, feed rivers, and hold the history of Earth's climate within their layers. This video goes over the many different types of glaciers and all that comes with them. Glaciers are not simply frozen blocks of snow. They are records of time. Within their layers are trapped air bubbles, remnants of past atmospheres, evidence of volcanic eruptions, and microscopic particles revealing how the climate has changed over thousands of years. By studying glaciers, scientists can uncover stories of Earth's past and clues about its future. Some glaciers vanish within decades, while others last for thousands of years. Some grow thicker and longer, influenced by local precipitation and temperature, while others recede quickly. So, what exactly is a glacier? Well, at its simplest, a glacier is a persistent body of ice that forms when snowfall accumulates year after year, compressing into dense ice under its own weight. Unlike seasonal snow, which melts in spring or summer, glaciers can last for decades, centuries, or even millennia. Over time, the accumulated snow compresses into ice, and under pressure, this ice begins to flow downhill. This movement is slow, sometimes only centimeters per day, but over centuries, glaciers can carve valleys, mountains, and ridges called artes, and leave behind moraines, large piles of rock and debris pushed forward by the ice. Glaciers are incredibly dynamic. Some surge forward in sudden movements, called glacier surges, traveling several meters per day for short periods. Others retreat gradually, losing ice as they melt faster than new snow accumulates. Their size, movement, and behavior depend on many factors, including temperature, precipitation, slope, and the presence of meltwater beneath the ice. There are several main types of glaciers, each with unique features. Valley or alpine glaciers are the classic mountain glaciers, forming high in elevation and flowing down valleys. These glaciers often carve dynamic landscapes, creating U-shaped valleys and jagged peaks. Famous examples include the Mer de Glace in the French Alps and the Franz Josef Glacier in New Zealand. Alpine glaciers are especially sensitive to climate change because even small temperature increases can speed up their melting process. Ice sheets are massive, continent-spanning glaciers. Greenland and Antarctica are the only remaining ice sheets on Earth, and together they hold more than 99% of the world's freshwater ice. Ice sheets can be several kilometers thick, and their enormous size means that small changes in the ice mass can significantly impact global sea levels. Unlike alpine glaciers, ice sheets flow outward in all directions, and their behavior is influenced both by climate change and the ocean below. Ice caps, however, are smaller, dome-shaped glaciers that often cover highland regions. These include the Vatnajökull ice cap in Iceland and ice caps in southern Patagonia. Ice caps feed many outlet glaciers that extend down valleys, providing fresh water and shaping landscapes as they move. These are often called glacial tongues. Piedmont glaciers form when valley glaciers spill out of mountains and spread across flat plains, creating wide lobes of ice. Alaska's Malaspina Glacier is a prime example, covering hundreds of square kilometers at the foot of the mountain. These glaciers show how ice can transition from steep mountain flows to broad, sprawling ice sheets. Tidewater glaciers end in the ocean and often calve large icebergs into the sea. The Columbia Glacier in Alaska is a prime example, retreating rapidly and producing massive icebergs that drift into Prince William Sound. Tidewater glaciers are highly sensitive to ocean temperatures. Warming seas can melt the ice from below, speeding up their retreat. Now that you've got your bearings, let's get into why glaciers are changing. In Alaska, the Columbia Glacier has retreated more than 20 kilometers since the 1980s, losing hundreds of meters of thickness in some areas. Each year, it sends massive icebergs into Prince William Sound, and its rate of retreat has accelerated due to warming ocean temperatures, thinning ice, and reduced snowfall. The Mendenhall Glacier, located near Juneau, has retreated over a kilometer in recent decades, leaving behind a barren valley dotted with newly formed glacial lakes, streams, and vegetation that is slowly recolonizing the exposed rock. These glaciers illustrate how quickly massive ice masses can vanish when conditions shift. In the Himalayas, glaciers in the Khumbu region near Mount Everest are also retreating rapidly. These glaciers are critical water sources, feeding major rivers such as the Ganges, Brahmaputra, and Indus. Tens of millions of people rely on this water for drinking, irrigation, and hydropower. Some Himalayan glaciers have thinned by more than 40 meters over the last 50 years, altering river flows and increasing the risk of glacial lake outburst floods, or GLOFs. These sudden floods occur when water trapped behind ice or moraines is released, causing devastating effects downstream. In South America, the Patagonian glaciers are notable examples. Gray Glacier has retreated several kilometers over the past 50 years, leaving behind a barren valley and newly forming lakes. Meanwhile, the Perito Moreno Glacier has remained relatively stable, resisting the general trend of retreat, illustrating that even neighboring glaciers can respond differently to the same climatic conditions. Scientists attribute these differences to variations in precipitation, temperature, and local geography. The Patagonian glaciers highlight how complex glacier systems can be, even in the same region. Kilimanjaro, Mount Kenya, and Rwanzi Mountains are often referred to as the Mountains of the Moon, and are home to equatorial glaciers that have persisted for thousands of years. These glaciers survive due to their extreme altitude, despite the surrounding tropical climate. However, even these glaciers are retreating rapidly. Kilimanjaro has lost more than 80% of its ice coverage since the 20th century. The reasons glaciers retreat are complex. Rising global temperatures cause ice to melt faster than snow can accumulate. Darkened surfaces due to soot and black carbon from pollution and wildfires increase the absorption of sunlight, accelerating melting. Volcanic ash deposits can have a similar effect. Ocean warming contributes to the rapid retreat of tidewater glaciers, which melt from beneath. Even minor changes in local microclimates, such as a cloud cover, precipitation, or wind patterns, can influence whether a glacier advances, retreats, or remains stable. Despite the widespread retreat, some glaciers are still advancing. In Antarctica, certain outlet glaciers are thickening due to increased snowfall. In Iceland, portions of Vatnajökull outlet glaciers are moving forward, even as global temperatures rise. Local cooling, increased precipitation, and volcanic activity beneath ice sheets can contribute to glacier growth. These examples remind us that glaciers are dynamic and highly responsive to both local and global conditions. Glaciers aren't just wonders, they're lifelines. Many of the world's great rivers, from the Ganges River in Asia to the Santa River in South America, are fed by glacial melt. These rivers supply drinking water, irrigation, and hydroelectric power to millions of people. When glaciers retreat, that balance shifts. At first, more meltwater may flow, swelling rivers and triggering floods. But as the ice diminishes, long-term water supplies shrink, disrupting farming, energy generation, and urban water systems. The effects ripple far beyond the mountains. Glaciers directly sustain economies, ecosystems, and communities. Their disappearance also reshapes the planet itself. Melting glaciers are a major driver of rising sea levels. The complete loss of the Greenland ice sheet could raise global seas by more than 7 meters, while the West Antarctic ice sheet could add 7 more meters. Even smaller changes matter. Each year of accelerated melt threatens coastal cities, low-lying islands, and fertile deltas with flooding and saltwater intrusion. Glacial retreat can also unleash hazards such as glacial lake outburst floods, sudden violent torrents when unstable ice or moraine dams give way. In regions like the Himalayas and the Andes, such floods have wiped out villages, farmland, and infrastructure. Ecosystems, too, feel the loss. Cold glacial meltwater supports fish, insects, and alpine plants that can't survive warmer conditions. As the ice recedes, these habits vanish. Water temperatures rise, and entire species could be displaced or lost. Even oceans are affected, as massive freshwater pulses from melting glaciers alter salinity and ocean currents, reshaping marine ecosystems thousands of miles away. Glaciers have played a significant role in human imagination, culture, and folklore. In Icelandic sagas, glaciers are often depicted as living, powerful entities shaping the land and influencing human lives. Indigenous people in Alaska, the Himalayas, and the Appalachians have their own legends about glaciers, often describing them as dangerous spirits or divine forces. These stories reflect the awe and respect humans have for glaciers throughout history, portraying ice not merely as frozen water, but as a potent natural force. Explorers and mountaineers have long been captivated by glaciers too. Early alpine pioneers carefully mapped glaciers in Europe, noting their movement, seasonal changes, and the landscapes they carved. In Antarctica, explorers like Ernest Shackleton encountered glaciers so vast and unpredictable that they often took days to months to cross. In the Himalayas, Mount Everest expeditions relied on knowledge of glacial conditions to navigate the Khumbu icefall, one of the most dangerous sections of the climb. Some glaciers that once existed have now entirely disappeared, and studying these lost glaciers provides an insightful insight into past climates. The By studying their remnants, scientists can understand the pace and impact of glacial retreat and infer the climate conditions that sustained them. Even seemingly tiny temperature changes can have enormous effects on glaciers. Iceland provides a striking example. The greatest extent of Iceland's glaciers in modern times occurred at the end of the Little Ice Age, roughly around 1890. At that time, glaciers covered approximately 11.6 to 12% of Iceland's land area, over 13,000 square kilometers of ice across the volcanic island. Since that maximum, the glaciers have retreated dramatically. Today, Iceland has lost more than 2,200 square kilometers of ice, about an 18% reduction from the Little Ice Age maximum. Remarkably, this massive retreat occurred with an average temperature increase of only about 1 degree Celsius over the last 130 years. A change so small it might seem inconsequential, but for glaciers, systems finely balanced between accumulation and melting, 1 degree is enough to tip the scales. To put this into a broader perspective, consider the temperature differences separating us from major glacial events in Earth's history. Today, we have an average surface temperature of roughly 15 degrees Celsius, but during the last glacial maximum, about 20,000 years ago, it was roughly 5 degrees Celsius colder. This relatively modest difference has led to massive ice sheets over North America and Northern Europe, covering millions of square kilometers and drastically reshaping the planet's surface. Go back to the snowball Earth era over 600 million years ago, and the global temperatures were only 10 degrees lower. Compared to these extremes, the 1 degree change that caused Iceland's glaciers to shrink by thousands of square kilometers seems minor, but it illustrates how glaciers act as sensitive thermometers of planetary change. Some glaciers, once connected during the Little Ice Age, have now fragmented, with their ice retreating into isolated patches that barely persist above the volcanic bedrock. In a single generation, humans have witnessed a transformation that took Mother Nature hundreds of thousands, or millions of years to create. This sensitivity is mirrored worldwide. Alpine glaciers in the European Alps, the Rockies, and the Himalayas respond to fractional degree warming with rapid retreat. Tropical glaciers, such as Kilimanjaro's ice fields, have already disappeared or are near disappearance, even though regional warming there is smaller than in temperate zones. Small changes, compounded over decades, are enough to push these fragile ice systems past the tipping points. In essence, glaciers act as natural amplifiers of climate change. They provide an immediate, visible, and measurable signal of even minor shifts in Earth's energy balance. Iceland's 1 degree warming, the retreat of Kilimanjaro, and the shrinkage of Alaskan glaciers all demonstrate that glaciers are extraordinarily sensitive indicators of both regional and global temperature change. These changes are not just historical or academic, they directly influence sea levels, freshwater supply, ecosystems, and local communities. Today, a difference of just a few degrees over the next century could reshape the distribution of ice worldwide, causing large-scale retreat around the entire world. The United States is home to a remarkable range of glaciers, spanning from the icy heights of Alaska to the remnants of glaciers that once existed in the eastern Appalachians. In the western United States, the Rocky Mountains, Sierra Nevadas, and the Cascades host smaller alpine glaciers, many of which are retreating rapidly. Glacier National Park in Montana, often known as the crown of the continent, once contained over 150 glaciers in the early 20th century. Today, fewer than 30 remain. This is not an extreme example. This is the average. These glaciers are iconic examples of how modest global warming can dramatically impact ice masses. The Sierra Nevada of California, though less famous for its glaciers than Alaska or Montana, contains remnants of past ice, including perennial snowfields and small alpine glaciers, which slowly feed mountain streams and reservoirs. These western glaciers continue to shape landmasses, feed rivers, and provide critical fresh water to surrounding regions. Predicting future glacial changes relies on climate change models and scientific projections. By 2100, most tropical glaciers, including those on Kilimanjaro, are expected to vanish entirely. Alpine glaciers in Europe and North America are projected to lose 50 to 80% of their mass, depending on emission scenarios. In polar regions, West Antarctic glaciers are at risk of rapid collapse if warming continues. While snowfall increases, these projections underscore the urgency of understanding and mitigating climate change. Beyond studying current glaciers, scientists and engineers have considered the possibility of geoengineering or glacier restoration projects, though these ideas remain largely theoretical. One proposal involves artificially increasing snowfall or reflecting sunlight to reduce melting. Others suggest redirecting meltwater to feed shrinking glaciers or using large-scale cooling methods to stabilize ice. While such projects are intriguing, they come with massive technical, environmental, and ethical challenges. Altering glaciers on a large scale could have unforeseen or ecological consequences, disrupt local hydrology, or interfere with natural ice dynamics. Nevertheless, these ideas highlight the lengths to which humans might go to preserve glaciers in the face of rapid climate change. As we look to the future, glaciers remind us of the consequences of climate change and potential for human intervention. They offer lessons in resilience, adaptation, and the complexity of natural systems. Their retreat highlights the fragility of ecosystems and human societies depend on ice-fed water sources. At the same time, their persistence in some regions demonstrates the power of local conditions, resilience, and natural variability. Whether shrinking, advancing, or stable, glaciers continue to be critical indicators of planetary health. The story of glaciers is that of human fascination and exploration. Early European scientists meticulously mapped alpine glaciers, while adventurers in the polar regions risked their lives to explore uncharted ice. The Himalayas, the Andes, and Greenland became sites of daring expeditions, often accompanied by detailed scientific observations. These expeditions provided not only maps and measurements, but also inspiration, folklore, and legends that continue to influence culture today. Glaciers are not just scientific curiosities. Their changes affect ecosystems, societies, and global systems in ways that extend far beyond the mountains or polar regions where they exist. Understanding glaciers requires a combination of science, culture, and storytelling, bridging knowledge and inspiration. In conclusion, glaciers are ancient, dynamic, and vital components of our planet. From the massive ice sheets of Greenland and Antarctica to the rapidly retreating alpine glaciers of Montana and Patagonia, from the lost glaciers of Appalachian Mountains to the small equatorial ice caps of Kilimanjaro, glaciers tell a story of Earth's past, present, and future. They are archives of climate, sculptors of landscapes, and indicators of planetary change. They melt, grow, move, and surprise, connecting humanity to the rhythm of the planet. With this, finally, you can say why glaciers are changing, and fast.